Hi, my name is Vinay, and in this video we would be demonstrating the velocity control of a DC motor using 20sim software. I would be using a 4C toolchain which will be used to convert your control model into a C code and to be downloaded into an online board. I will be using a DC motor coupled with an optical encoder for the velocity control. So let me start with opening of the model file. So there is my model. So on the right hand side part, you see this part of the model is the mechanical description of the setup, where I have a DC motor coupled with a gearbox having some inertia, backlash, and a little bit of bearing. The feedback is taken from an optical encoder. So the resolution I'm using of the encoder is 9840 counts per revolution. So the feedback is given to a velocity controller, where I'm having this model for the control reference. So where I have a motion profile, so this guy decides what kind of velocity profile I should apply to my motor. The input is given to a PI controller, who in turns keep the output velocity in control. The feedback to the PI controller is being taken from an encoder, which is attenuated by the number of counts, converted to velocity conversions, because revolution has to be converted into velocity, and then the feedback is given to this block, which is a plus minus block, and the PI controller just gets the error out of it. I'm just using a little bit of feed forward for quite stable control. There is a signal limiter just to keep the output in the limits of plus minus 1 range. Okay. So let's simulate this model. So thereby you can see that the green one is the reference velocity, and the purple line which follows very closely to my reference velocity signal. The stroke is given as 30 or 300 rpm. Okay, let me change the stroke or some of the parameters of the velocity controller. So let's say, okay, I keep the stroke same, and I just change the PI controller some control fraction. Okay, let's say instead of 0.05 I make it 0.001, so it's a very low gain. So you can see that the motor is not able to keep the reference velocity in match with the simulation model, and this guy is not following exactly as the reference model. But let's say still I want to download this model and see the result, so that we can compare both the results of actual and the simulation model. Just to remember that we will set it back to the original tuned value of 0.05 of the KP in PI controller. Okay, now we need to download this velocity controller in the hardware. For this, we can take help of 4C toolchain. So I just go to tools, real-time toolbox, C code generation, and I take help of 20sim 4C toolchain, because 20sim can convert any control model into a C code, but then downloading a C code into a given hardware platform is quite a lengthy process. So 4C toolchain comes as a rescue and does a beautiful job of saving time in the execution of the model in the hardware. So that runs a 4C toolchain. I can select the hardware as TS7300 because that is the hardware setup I'm using. 20sim supports few more other hardwares. So it connects with the online board using an Ethernet link. So I'll just say apply. So as is a 4C toolchain, the name implies configure, connect, compile, and command. So we have done the configuration. Now we have to do the connection part. So the model has only 2 ports: input, the encoder input, the output applied to the PWM channel of the motor. So the input, I can select the channels as XDI1 quadrature counter, and the output of the model I will connect to the PWM port that is HDI1, and just say apply. So the model will turn green, and now the next step is compile. So 20sim will compile the generated C code for the target board specified, which just take few seconds to do that job. It's quite fast. Now the next is command. So here you can change the discrete time interval or the frequency. You can change the step finish time. Let's say I just set it to 8 seconds. It will run for 8 seconds. And let's say you want to run the model, but along with the recording or the logging of the variables. So you just go to log, and you can ask him to select the variables. So on the left hand side, it's a much better browser. So we want to record, okay, I just show you the model back. So I will record the output velocity of this motion profile and the feedback, the velocity feedback, this signal generator, signal monitor, I will be monitoring it. Or you can just say that it is the output of the SVF model. So I just take the velocity feedback and just say input, I say log it, and motion profile, its velocity output, I will log it, and I'll run this. So here the model is running in my hardware. You can hear the sound of the motor, and you can see that this guy also follows in the same way what was your simulation. So let me open it. So you can see side by side the simulation and the actual run. They are coming almost the same. Okay. So now let's say I want to tune up back it to more accurate control of the velocity. So in simulation I'll just show you it was 0.05 was my tuned value of the velocity control. So this is the same I would do over here in 4C. I just go to PI block, and over here I can make changes in any of the model parameter. I just say apply. So here my KP has turned out to the same value of 0.05 in simulation. I upload. So you heard the sound of the motor, and now we are logging the results and we will be plotting it here. So yeah. So you can see side by side it is the same result of the simulation model, and in the actual run model they are coming quite close to each other. I just add the video post to it in the hardware running with the same parameters. Guys, we are running an velocity control of a DC motor. So that is the hardware I'm using it. So that's my DC motor, which is a 300 RPM DC motor coupled with optical encoder at its back. For execution of the model, I'm using an ARM9 board and coupled with a driver card, having a driver for the DC motor and interface for the optical encoder. There you are. Okay. So this board gets connected with the LAN port to my laptop. So first of all, I have set the PI controller value as 0.001. So that was the KP that we run for the first time, and then later 0.05. Okay, so I just run this model, and at the same time we see the model. So there you see that motor rotates and declines within velocity, and you can see that was the result what we got. Now I change the PI model, and the KP I set it back to 0.05. Okay, and apply it. Okay, I've set the KP as 0.05, and now I run the model again. Just a bit closer. Yeah, and there you are. So it accelerates to the stroke of 30, that is around close to 300 RPM, and you can see that it got the same result. Yeah. So that was the velocity control of a DC motor using 20sim setup. Thank you.